Before we get started, I wanted to begin just with one of my favorite examples of practical analytics and how it influences our everyday life. So I spent a lot of time traveling for my work, and I've really grown to appreciate the simple, meaningful, actionable predictive analytics that Uber provides. If you don't know what Uber is, it's a ride-sharing system, and it's kind of like being able to call a taxi from your phone, except it's more than that, because when you make a request from Uber, they know your GPS location of your device. And they also know the GPS location of drivers who are around you. And Uber uses your GPS location and the GPS location of the drivers around you to estimate how long they think it'll take to get a is now available as an Apple Watch application. So what you're seeing here is a picture of my watch yesterday, and at that time, Uber said it would take 5 minutes to get a driver to me, and it was all based on predictive analytics of my location, the location of the drivers around me, the routes between me and those drivers, the travel time, the time of day, and perhaps past travel times of those routes. And all of that information is kind of put together in this simple number, 5 minutes. And this is great because it's super actionable. If I am happy with that number, I go ahead and hit that request, and a driver shows up in about 5 minutes. If I'm not happy with that number, maybe it's too big, maybe I just cancel my request and call a cab. And I've done that before. And it's just a great example of how Uber is taking all of this data about me and the drivers, compiling it into a very simple, actionable number that's delivered right to my watch. And it's not just Uber. We live in a world where predictive analytics is pervasive. So when you log into Amazon or Netflix, this is what Amazon and Netflix thinks that I want to watch based on the viewing patterns of the account that I use. And it's interesting, I think it's pretty obvious probably to many people that it's not necessarily me who's watching these videos. What's going on here is Amazon is taking the buying and viewing patterns of me and comparing them with users who have similar viewing patterns and making suggestions based on those patterns. And what happens here is that my kids log in on the weekend and they watch all sorts of cartoons, and Amazon and Netflix both think I have a strong interest in watching a ragtag group of cartoon puppies solve problems. That's what Paw Patrol is. But the truth is I'm not really interested in these predictive analytics. And it's an interesting thing to think about is what are the assumptions that we make about the underlying data as we use predictive analytics. And I think we'll ponder some of these questions about what it means for healthcare a little bit later in the presentation. We're going to have another quick poll question. So how important are predictive analytics for the future of healthcare? Not at all important, low importance, neutral, moderately important, extremely important, or unsure or not applicable?
Okay, Eric, while we're having everyone respond to those, I'd like to apologize to everybody. The audio, we had a couple of audio issues. We think we've got those sorted out. We said this is new software for us, so we appreciate your patience with us. All right, let's go ahead and share the results of our poll. Well, we're showing 75% extremely important. I guess that's why they joined the webinar today.
I was going to say, it sounds like a little bit of a selection bias, but it is. I think it is important, and we'll talk about how we can lower the barrier to doing predictive analytics in healthcare.
All right, we're just getting back to share that screen.
All right, as we move into healthcare, so first of all, let's just high level, predictive analytics is about using pattern recognition, just like we talked about with the Amazon and Netflix examples. There's patterns in that data that they're using to predict future events. We can apply that to healthcare, but it's really important that predicting something, to understand that predicting something is not good enough. You must have the data to act and intervene. And especially in healthcare, the organizational wherewithal to intervene. It's one thing to predict what videos I might want to view next or what things I might want to buy next. It's a different thing to start recommending care based on predictive analytics. So in healthcare, the stakes are higher, but the rewards are potentially much greater. And it's important for an organizational to buy into that risk balance, and also to ensure that the analytics are incorporated in an appropriate way into the very complex operations of a healthcare organization. So it's definitely a different game. at this point, I wanted to talk, just outlay some definitions, and we have a few definition slides here in the presentation, and I just wanted to kind of clarify these as we move along, because I'll be using some jargon in the presentation, and I think it's good to get everybody on the same page about what that means. So we often hear machine learning and predictive analytics in the same breath, and sometimes even mentioned synonymously. So machine learning explores the study and construction of algorithms that can learn from and make predictions on data. Then within the field of analytics, using machine learning is a method used to devise models that lend themselves to prediction. This is predictive analytics. So the way that I like to think about it is that machine learning is a technique that's used in predictive analytics. There are other ways to do predictive analytics, but machine learning is by far the most pervasive, popular, and growing method right now for predictive analytics. That's why you often hear them mentioned in the same breath. Predictive analytics isn't completely new to healthcare. So when going all the way back to 1987, the Charlson Index is actually a predictive algorithm. It's designed to predict the mortality of a patient with multiple comorbidities. And the Charlson Index was done by a group that took data from numerous patients, classified their conditions into comorbid conditions, and they used a fairly narrow set of data, so fairly easy to get set of administrative data. Then they counted those comorbid conditions and ranked them based on their severity. And they combined that combined comorbidity score with other information about the patient, such as their age, to develop a relative risk that that patient was going to die in the next 10 years. So it is a predictor of mortality, and it's actually gained widespread popularity. We hear a lot about Charlson Index still today. The LACE Index is another example of predictive analytics, and LACE is meant to predict readmissions. And the LACE group took data from all across the country and developed a model that predicts readmissions based on length of stay, acuity, comorbidities, and ER utilization. That's what LACE stands for. And the group basically took data from a large number of different organizations contributing their data, and they developed this model that uses those inputs to determine the patient's risk of readmission. And it also has gained widespread popularity, and we hear of a lot of organizations that are implementing LACE. The interesting thing about these models is that while they're very good because they allow organizations without a deep machine learning capability to do predictive analytics and to do it on a smaller, easier to get set of data, there are problems with these models. And we're showing here two issues that have come up with these models. So, and these are just two of many. So what you see in the top headline is, the top citation is that they were using LACE to predict readmissions for CHF patients, congestive heart failure patients. And the next one, they were trying to use LACE to predict readmissions for older UK populations. And what they found in both of the conclusions, it says that LACE was not a good predictor for both of these specific populations. And part of the reason for that is that when the LACE model was created, they were using data from all different kinds of patients from all across the country. And we know, for example, that the factors that drive an appendectomy readmission are quite different than the factors that drive congestive heart failure readmission. In the LACE model, all of those are mixed together, and as soon as you start looking in specifically and using LACE to try to predict a specific population, you lose your predictive value. So these general models, while they're helpful to get people started, they lose their predictive value as we start to look more and more into specific populations. And anybody who's working in healthcare today knows that we're doing a lot of that. We're looking at looking into how do we care for this specific population. So those models don't hold up so well for that use case. So what's happened since these models came out in 2010? First, we talked about on the last slide the limitations on those models. While they're good to get started, they lack in their ability to predict specific populations. Next, data availability has grown a lot since 2010. We've been lucky enough to be a part of organizations that are investing in data warehouses. After the big investment in electronic health records, a lot more data became available. And the premise of the index models is that they're using a narrow set of data, but now organizations just have access to much deeper repositories of data. Again, we've been lucky enough to be a part of that and see that play out. There's also more advanced analytics capabilities. So the basic understanding of how to use data to improve business process and to improve care has been taken a larger part of our national focus as well. Organizations are routinely using data to improve healthcare, and they're starting to ask that next level of questions. So we typically start with retrospective analytics. So where have we gone wrong in the past, and how can we fix that moving forward? Now organizations are asking more mature questions about, help me get ahead of my problems, and predictive analytics are of course, a big part of that. And finally, we have much better machine learning tools since then. So even in that relatively short amount of time, there's been a huge explosion of open source tools, of online education that help to spread this machine learning and how to do machine learning. And so those better tools are also part of this increased interest in machine learning-based predictive analytics. So we're going to ask another poll question. What's the biggest barrier to implementing predictive analytics? We're lacking the right people or skills. We don't have the right data or technical tools and infrastructure. We don't have the executive support or budget. Past efforts have failed to show results. Other, or unsure or not applicable.
Right, we'll give some time for folks to respond to the poll. And we'd like to remind everyone, we have had a few questions about the slides. We'd like to remind everyone that we will be sending out an email after the event with links to the recorded on-demand webinar as well as the slides as well. So let's go ahead and look at our results.
Okay, it looks like organizations, the top two responses are people or skills and the right data or technical tools. And hopefully those points are well addressed within the rest of the presentation. And executive support or budget is also a very big factor, and we'll hopefully have some information that can help convince executives that this is a good thing to do as well. So the main message of all of this presentation is that predictive analytics is easy. It's at least easier, and part of that's due to the explosion of tools. But what organizations are truly struggling with is making predictive analytics routine, pervasive, and actionable. And that's what we want to talk about today, is how do we take predictive analytics and make it something that's easier to do and routine for an organization. The typical current state of predictive analytics is still not necessarily optimized for operationalization. What happens is you've got data scientists, and they may have access, they may have read access to a data repository. And the first thing that they do when they have a predictive model that they want to develop is they write a really big query against that data source, because they need to get all of the data points they think they're going to need to make a prediction. And they know they're going to have to manipulate that data. So they write this really big SQL query, then they bring it into their tool of choice. It could be Excel, it could be SAS, it could be R, but the idea is that they get all that data into their tool because that's where they feel comfortable manipulating data. And then they do that data manipulation. They get that data in a state that's ready to be used in a predictive model. And again, they're using a tool outside of their analytics environment to do this. Then they apply the tools and algorithms. So examples, SAS, Weka, R, and Python, all of these tools are tools that are available to take that data and turn it into a predictive model. And then once they've developed a predictive model, there's a big question mark, two questions usually. Number one is, how do we move this into production? And then number two is, how do we actually get it to improve care? Or how do we get it to actually enhance a decision? So that's oftentimes a big question. And we've seen that a bunch of times where a good predictive model is developed, but it's never really deployed. And the point today, we'd like to just talk about 3 recommendations. And the way we'll be structuring the rest of the presentation is about these 3 recommendations. Number 1, fully leverage your analytics environment. And we'll talk about what that means. But in a nutshell, don't do a lot of data manipulation outside of your analytics environment, because then it becomes a silo and very difficult to reuse. Standardize tools and methods and create production quality code that you feel comfortable putting into production. If you develop a good model, the logical next step is going to be to put it in production. So having really good code to do that is very important, and also to have standard methods with your team. And this one is last, but it should really be first because it's the most important of all of these points, is to deploy your models with a strategy for intervention. Make sure you know who's going to use the data to change what they're doing or to help make a decision, and how that's going to be presented with them. That's the most important point of all this, and we'll talk about what that looks like a little bit later in the presentation. So let's talk about fully leveraging your analytics environment. Here's another piece of jargon. In predictive analytics, a feature is simply an input parameter. Just think of it as an input to one of your data models. And in machine learning, we call it a feature. So when you hear me use the word feature, just think of these are the inputs to the model that I'm trying to generate a prediction from. And this definition is from Wikipedia. And let's think about what an analytics environment is. An analytics environment or data warehouse you can think of as almost like a chock full of features. You've got a bunch of data there, but it's not always just sitting there in raw format. You've got things like clinical registries, you have comorbidity models, you have calculations on readmissions and length of stay and other calculated fields. So all of these make great feature inputs to models. But it's really important to understand that read-only access is not enough. Data scientists and the folks who are generating predictive models need to be able to create their own features in the analytics environment. We'll make a strong case for that here. To illustrate the point, we're going to explore a polypharmacy feature. And this is a feature that we developed as an input to one of our models. Our data scientist was developing a model, one of our data scientists was developing a model for predicting complications in diabetic patients. And if you don't know what polypharmacy is, the New York Times here represents it as the ever-mounting pile of pills. Quite simply put, it's the number of medications that a patient is on at any given point in time. And there's good examples in the literature of polypharmacy being a good predictor of specific outcomes. So this data scientist wanted to use a polypharmacy feature in his model. And when he looked at the medication data, though, it was a little bit messy. And I'm sure, given the number of data architects and analysts we have on the call, this shouldn't come as a surprise that there's messy data underneath the hood in the data warehouse environment. And what you see on the left-hand side is a table of medications. And for every patient medication pair, there's a start date and an end date, the date that a patient started a specific medication and the date they ended up on. You can see on the far right-hand side that there's several nulls. So the end date is not known in cases, and it's actually missing data that can actually be very damaging to a predictive model. So how do we clean that up? Well, we've got to understand what's going on to create those null values. In some cases, the patient died before the end date. And in other cases, the patient took a one-time dose where they were not the end date wasn't put in because there was a single dose of the medication. And finally, there's yet another case where the patient just hasn't reached the end date yet. They're still on the medication. So understanding all of those business rules helps our data scientists to fill in appropriate missing end dates and create what you see on the right-hand side here, which is what an input to a predictive model looks like. It's very clean, and it gives us that polypharmacy count. So for every patient encounter for any point in time, we can easily tell how many medications a patient was on. And this is an example of what we call feature engineering. Feature engineering is the process of transforming raw data into features that better represent the underlying problem to the predictive models, resulting in improved model accuracy. And feature engineering, in our opinion, is one of the most challenging and interesting parts of developing predictive models. It's also recognized by folks out there on the internet that much of the success of machine learning is actually success in engineering features that a learner can understand. So feature engineering is an absolutely critical part to data science and predictive analytics. We can't underscore that point enough. Other examples of feature engineering, and I'm sure the data architects and data analysts on the phone will recognize how some of these things sound really simple, but they're actually a little bit more complicated to put together than you might think. So the number of ER visits in the last year, fairly simple. The number of line days that a patient is on, Sometimes the underlying data presents a challenge in calculating that. The number and types of comorbid conditions. How do you classify those comorbid conditions? Almost any input to a predictive model will need to be engineered in some way. And the ability for data scientists to engineer features is critical to the success of predictive analytics and a machine learning strategy. And remember, the point of this section is to fully leverage your analytics environment. And one of the main reasons why we say that is because the analytics environment is the best place to engineer features. The data scientists have to be able to promote efficient reuse of the engineered features. That's one great example. So that if we go back to that polypharmacy example, that polypharmacy table is now sitting in the data warehouse and available for other models to use. So by using the analytics environment to do our feature engineering and not doing it in a siloed tool, we're promoting reuse of all that great work. Secondly, the data warehouse has standard tools to operationalize and run these on a nightly basis. We call it ETL, or extract, transform, and load, and those tools are very valuable in productionalizing that code. It becomes much easier to productionalize than in a script in one of the machine learning languages. So going back to our 3 key recommendations, remember the first was to fully leverage the analytics environment. And the next is to standardize tools and methods using production quality code. As you start to put forth a data science, machine learning, predictive analytics strategy, you need lots of smart people to do this. This shouldn't be a surprise. And the 2 roles that I want to talk today they're similar but different roles. So the data scientist formulates hypotheses about features driving a predictive model. The data scientist is the one who's talking to clinicians and trying to understand the underlying causes of what is trying to be predicted. The data scientist is doing what we call experiments and trying various models to determine the best approach for prediction. And the data scientist is assessing the model output and looking at the accuracy and trying to decide on what the best approach is. The machine learning engineer, like I said, is a similar but different. So the machine learning engineer has to have a lot of knowledge of data science, but one of the challenging things is to find somebody who has a knowledge of data science and a knowledge of software engineering best practices. Because remember, we're talking about generating production quality code. And one of the biggest impacts we've had on our group was when we hired Levi, who's got a great machine learning engineer approach. He understands the data science, and he also has a knowledge of software engineering best practices, and that's really helped us to scale. And we'll talk about what we mean by scale. But a machine learning engineer is a wonderful thing to have, and we'll talk about the fruits of our machine learning engineering efforts a little bit later. So in order to talk about what kind of code you need, I think it's good to talk a little bit about the predictive analytics processes. And what is it that a data scientist is doing that we want to try to operationalize? And there's 2 pieces to this. One is a development process. And let's use the example of a readmission prediction. Let's say we're trying to develop a model to predict readmissions. The data scientist is going to, first of all, identify which patients were readmitted and which patients weren't. That's important to understand what the outcomes were. And then they're going to gather 30 to 40 feature inputs, and this is where hypothesis generation takes over. They're hypothesizing what are the 30 or 40 most likely things to drive readmissions. And that data set, the 30 to 40 input features and the outcome, is then split into 2 pieces. One we call the training set, and one we call the test set. And the training set is what we crunch all the numbers on, and that's where our model is generated from. The test set is what we use to measure the performance of that model. So it's important to hold back some data so that we can see how well our prediction would have done on predicting the items in the test set. And so the data scientist is running multiple algorithms on that training set. They're looking at lots of different combinations of features and lots of different algorithms. And for each one of those, they're measuring the performance and deciding what the best model is. And it's an iterative process. So I've drawn this arrow going back to the beginning. Sometimes you need to go back to square one. But eventually you get to what you see in the orange box, where you've got a best algorithm and a smaller list of important features, usually around 10 or so. Once you've developed your model, you can then store those parameters for later use. Again, the development process is where the really intense computation, we're looking at millions of records and crunching numbers and looking for patterns in those and extracting the patterns. But once we get to a model, the next step is to run the model. And running the model is what occurs every day, multiple times a day, much less computationally intensive using the output of the development process. Now, if we're going to do a readmission prediction, we don't need to crunch numbers on millions of patients of data. We've done that in the development process. Now, it's a matter of looking at who are the patients who just came in. Let's get those 10 important features on those and run it one record at a time, calculate that prediction, and output it to the data warehouse. So running the model, much less computationally intensive, but this is the part that gets put in production and is run every day, either as part of an ETL process or part of a web service. We'll talk about the different ways that it can be deployed. These are just the two different things that the machine learning code should be able to address. In the development process, it's important to standardize on pieces of that, and running the model, that's where we want to have really robust tested code so we can put it in production. So I want to address why you would want a code base, a software to help you do this. There's a lot of tools out there that make it really easy to write some of these scripts, but it's important to focus the data science on the model development and not necessarily writing the code. The code is something that's standardizable, and the data scientist part, the questions that they're asking, what features do I use for input? How do I model those features in the database? How do I compare the performance of these two different models? That's the real value add of a data scientist, not necessarily writing code or possibly reinventing the wheel that somebody in their department may have already done. So having a standard code base also allows a team of data scientists to standardize the methodologies. It's a real problem if your data scientists are using two different pieces of software to create their models, and even more of a problem if they're measuring the performance of their models in different ways. How are you ever going to know what the best model is if we're using different yardsticks? So that standardization piece is important here too, to have an organizational code base that data scientists can use so that they're using the same methods. And then finally, the point that I've made a bunch of times, and I probably won't make much more than this, is that putting models into production really requires that production quality code. We don't want to put anything that might break into production. And as we were developing our machine learning code base, we thought it was really important to adhere to software development best practices. And software development best practices are used in the software development world to solve a lot of these same problems. So how do we create a robust, reusable code base? One of the first things that we did was use version control. And version control is used by software developers. It allows multiple developers to contribute code to a single repository. And by keeping it as a single repository, many people can be editing the same code base at the same time. And then there's tools to make sure that people don't step on each other's toes, and when there is a conflict, that it can be resolved. So it's really important for teams of data scientists to have version control with their code base. The other thing that's very important for this is unit testing. And unit testing has been used in the software development world for many, many years. And the idea of unit testing is that as software becomes more modular and more reused, it becomes a lot easier to accidentally break software. And a good software code base is efficient and it is reusing code, but you've got to make sure that as you make changes, your changes are not resulting in unexpected consequences. So unit testing basically does testing of all of the functions in your software to make sure that the output is as expected. So if I make a change to the software and that change, I'm not sure how it's going to affect the rest of the software. If I run the unit tests and they all run, I can be fairly confident that I haven't broken anything downstream. So these are some of the software development best practices that are required for having a good code base. There's also things like documentation. How do we get people to find all of the functionality available in the software? And continuous integration. These are all best practices that we use in the development of our machine learning code base. So if you're gonna embark on developing a machine learning code base, and please stay on for the entire presentation because we have good reasons why you might not want to develop your own. But if you are, there's a few technology choices out there. One is R. And R is a language that's been deployed and deeply entrenched in healthcare. I'm sure most of the analysts and statisticians are at least familiar with R on the call. It has been around for a long time, and because of it being an analytics environment, it is more familiar to analysts and statisticians. Python is another language that's out there. It's a fully functional software development language. The language itself isn't new, but a lot of the tools that have been developed for machine learning are newer, and there's lots of momentum behind Python. As a matter of fact, a lot of the online learning based in machine learning uses Python as the language in which a lot of the new data scientists are being trained. And Python is more familiar to software developers and data analysts because it is kind of a full-featured software programming language. Azure ML is a cloud-based solution from Microsoft. Because it's cloud-based, it's very easy to set up and deploy. There's no installation required. You can just kind of create an Azure ML account and start creating models in the cloud. Because it's cloud-based and because we're in healthcare, the adoption of Azure ML is a little bit less than you might expect. And I've read some stories about organizations that are leveraging Azure ML for predictive analytics in healthcare, and they have to de-identify and scrub their data before they put it in Azure to do their models. And even in the example that I read, they were working with dates and they had to mask the dates. And if date is actually an input to your predictive model, to me that's a little bit risky to start manipulating dates to mask the data if you want to get a good predictive model. So for that reason, I think Azure ML hasn't seen the widespread adoption in healthcare that you might expect and that we've seen in other industries. There's plenty of other choices, but I think the industry right now is standardizing on R and Python, and that's where we've put our efforts. We have developed software in both R and Python to do our machine learning code base. And the reason why we chose both is R is probably more popular right now. There's support from major vendors like SQL Server, Microsoft SQL Server. Python is more of the up-and-coming approach, so we want to be ready for both of those, and our clients have different preferences as well, so we address both of them. So our code base includes tools for data ingestion. So we've been talking a lot about how do we leverage the analytics environment with our machine learning code. Well, we've got to be able to very quickly and easily get data out of that environment into our code base. So we have routines that load data from the database or a flat file. Date and time is important in machine learning. So we have tools that allow us to expand date times into things like day of the week, week of the year, make that really easy. Missing values can really complicate and make predictions not very good. So we have a couple of routines for dealing with those in different ways. And by all means, the way that you deal with missing values is different for different models and different use cases. So we want to provide functions for that. We also provide a large tool set around the model development. This is all the number crunching that we talked about in that workflow of a data scientist. So splitting that data between test and training, doing feature selection. How do we get from 40 features down to 10 features? And then, of course, the machine learning algorithms themselves. What are we running on the data? Random forest is a very popular algorithm. Lasso is a regression-based method. And then mixed models are coming. Those help us deal with longitudinal data in healthcare easier. And K-means clustering, which we will be using extensively next year in our code base as well. And then all of the tools to evaluate that performance and help the data scientists decide what's my best model. In addition to the development tools, we have analysis tools. So how do we generate a performance report for the models that we're creating? And then tools like to help identify with trend identification and be able to perform risk-adjusted comparisons are part of the analysis suite in our code base. The great thing about the software is that it's really helped us to scale people. And when we think about what are the big challenges in data scientists, and this has come up over and over again, the big challenges is that feature engineering piece and how do we represent the data. And it turns out data architects have great domain knowledge of how to do that. They've been moving data in healthcare and analyzing data and developing the routines to get data into different, transforming data into usable formats for years. They're also often looking for opportunities to advance their career and skills. And what we found is that given the right tools, data architects make incredible feature engineers. Given their years and years of experience in manipulating data, we're just applying them to a different problem. And it works really well. And then what our code has done is it has allowed data architects to easily get started in actually running predictive analytics algorithms. And this is a quote from one of our data architects who was using our software to create a predictive model in one of his products. And this is Peter Monaco. And he said, "One awesome thing about the output from the R package you put together is the output aligns perfectly with creating patient stratification algorithms. The fact that I feel comfortable running this stuff speaks to how easy you've made it. Thanks again, Levi." And he's thanking Levi, who's you're going to hear from in a little bit. But this is great. It allowed Peter to do what he does really well, get the data in a good format, and lowered the barrier for him to actually run these algorithms and do some of the work that a data scientist does. So we see it as very promising for helping us to scale our machine learning efforts across a large number of people in the organization. So now it comes time to put models in production. And we're going to talk first about how we move them into production from a technical standpoint, and then how do we move them into an application or view that can actually change business process or better yet, provide better care for patients. So modality number one is to put the model into production leveraging the ETL process. And this is appropriate if the prediction is not based on highly dynamic data, or if the intervention strategy is okay with some level of latency. So an example of this would be a readmission prediction. Typically, readmission algorithms are not based on highly dynamic data. They are based on data that's not changing super fast. So if we're pulling data on a nightly basis or every 12 hours, a readmission algorithm is generally going to be okay with that. And in this case, we just put the machine learning code in the middle of the ETL process. So we've got ETL to load the data sources. We've got ETL that data scientists or data architects create that load those engineered features, the inputs to the predictive model. And then we run that code that can easily grab those features from the database and output a prediction to the database. Our machine learning code can also write these predictions to the database. And this is how we've deployed several models. It's easy, and it just wraps right up with the ETL process. Modality number two is when the data is more dynamic. So an example of this would be sepsis early detection, where we're looking at changes in vital signs. And the intervention strategy, we can't wait up to 24 hours to intervene when sepsis happens. It's something we need to intervene faster on. So in this case, we can deploy the predictive algorithm as a web service. And the web service is receiving real-time features. So those changes in vital signs, or those vital signs, that's going to come in from a very dynamic setting. And we might still be using some historic features like what are the demographics, what's the age of the patient that we can pull from the EDW, and then the web service will be combining that live input with that historic data to run that machine learning code and then output the model back into the application. So this is definitely designed for more dynamic situations and more dynamic predictions. So going back to this point of deploying with a strategy for intervention, this is the real, I would call this the most important point of the presentation. So the idea here is how do we deploy and get these predictions to actually impact care. And we're going to talk about a little case study that we did with one of our clients on central line associated bloodstream infections, or CLABSIs. Approximately 41,000 patients actually end up with this condition. 41,000 patients in the U.S. per year, that should read. And actually 1 in 4 patients that get a CLABSI will die. So it's a very serious condition, and organizations are really struggling to keep up with this. There's great guidelines out there, evidence-based guidelines, for how to care for patients such that we reduce the likelihood of a CLABSI. And we worked with a client to develop retrospective analytics to look at their compliance. And it really helped highlight some problems, and they got really good at using the data to find problem areas and then developing interventions to fix those. So they develop the muscle memory of using data to improve their care and business processes. Then they said, okay, take us to the next step. Now we don't want to know where we failed. We want to know what's coming next. Who are the patients at high risk for CLABSI so that we can intervene with them? And so they came to Levi, and Levi and his team developed a predictive algorithm that's based on 16 features that predicts the likelihood that a patient's going to develop a CLABSI. We'll see what that looks like in a minute. It's important that every model that we develop and every model that we deploy comes with a performance report. And this performance report is not a highly technical report. And the idea here is that we're trying to briefly summarize what we're trying to predict, the variables that were considered in that, or the feature inputs that were considered in developing that model, what model we chose, and the accuracy of that model. And this report is not used for technical people, but this report is used for business or clinical people to help them understand that algorithm. The communication about what an algorithm does is extremely critical to the adoption of that model. When discussing models with clinicians, clinicians will adopt predictive analytics insofar as they understand it. If they don't understand what's going on, it's going to be a much harder conversation, because if you think about what clinicians do, they're running predictive algorithms in their head all day. They're looking at large amounts of patient data and boiling that down to hypotheses or conclusions about those patients. What we try to do with machine learning is standardize that. Typically, doctors don't do that all in the same way. So we help them to standardize it, and if they understand how we're doing it and it's close to what they're doing, they're much more likely to adopt it. The other point that we should make when talking about deploying predictive models is that complexity comes at a price, and it comes at an extreme price sometimes. So a regression model can often strike a balance between predictive value and interpretability. Regression models are one way to do predictive analytics, and there are more sophisticated machine learning algorithms that are much harder to explain. So if you have two models, a regression model and a more advanced model that might have marginally better accuracy, the regression model still may be the more favorable model to deploy because it's easier to explain. And in our code, we use a process called regularization that penalizes complexity. So the lasso algorithm is a regression algorithm that actually has built into it the ability for the model itself to tune itself and to favor a more simple model. And the way that Wikipedia says it is that enhances the prediction accuracy and the interpretability of the model. So super, super important. Complexity comes at a price, especially in the clinical setting for organizations that are new to predictive analytics. And what does it all look like? Now, this is the punchline. This is what predictive analytics looks like when it's put in front of clinicians and they're giving them the ability to make decisions based on this data. This is like the Uber telling me 5 minutes to a car on my watch. And what you see here is a unit scoreboard for our client who was doing CLABSIs. And I have to say, this was all generated on scrubbed, de-identified data set. But it actually fairly accurately reflects what the client was seeing in their environment. So I just want to make it clear that this is all de-identified data. But what you see here is in the green box, there are 12 patients who are active risk for CLABSI on this unit. And the unit reviews this dashboard multiple times per day. And what you see below in this list of patients here is the name of the patient, again, scrubbed, and the probability that they actually have a CLABSI. And the highest risk patients are at the top here. So the eye goes immediately to the patients who are at the highest risk. This top patient has a 64% chance of developing a central line associated bloodstream infection. And the important thing here is not to just give that number, but what goes on in this far right-hand column. This far right-hand column shows the risk factors that are driving that prediction. So, and moreover, it's not just the risk factors, it's what we call modifiable risk factors. So the patient's age is often a risk factor in their development of a CLABSI. However, there's not much a clinician can do about that. So what we do is we show the factors that the clinician can actually change or modify to get that patient to a lesser risk state. And in many cases, it's the number of days that they've been on a central line, the number of the placement of that line. There's all sorts of factors that drive it. And what the clinicians do is they look at this as a whole and decide, what can I do to reduce that patient's chance of developing a CLABSI? We are really excited about this. It's been deployed in a production environment at one of our clients, and we're working with them to understand long-term how will this affect the CLABSI rate for their patients. But this is just one example of what it means to put predictive analytics in the hands of clinicians who can make decisions of care based on this. The models we've built to date, this is just a listing of them. CLABSI is just one of many models. We wanted to focus on one high-impact example. But as you can see, we have a lot of algorithms that we've built to date that are driving decisions across the country, and lots more in development and lots of ideas. So this highlights, I think, the need for us to scale our machine learning and predictive capability. There's only so much that one team can use, and that's part of our strategy, is to use that software that we've developed to make it easier for lots of people in the organization to be able to do this. So we've got one more poll question. What are the top 3 important data sources to your organization in making predictions? Clinical EMR data, claims data, patient outcomes data, financial data, non-medical patient data, patient satisfaction data, or unsure or not applicable? All right, we've got that poll question up, Eric. And like everybody know, this is a multiple selection, so please select up to 3 if applicable. We'll leave this open for a minute. We'd like to remind everyone to please type in your questions or comments in the chat pane of your control panel. Got a lot coming in here. That's great. All right, let's go ahead and share the results. This is great. Okay, patient outcomes data. That's great. That's something that we're seeing a large trend in the industry as well. Clinical EMR and claims, of course, are very popular. The patient outcomes data is definitely a hot topic, especially patient-reported outcomes. How do we better measure those outcomes? And of course, that's what we're trying to predict, is outcomes in most cases. So, thank you for taking the time to respond to the polls. They're very insightful. So just to reiterate, our 3 recommendations: fully leverage your analytics environment, do the data manipulation in the data warehouse. It's easier to reuse, and it's easier to operationalize. Standardize using production quality code. So having your group using the same repository increases economy of scale, and it allows you to deploy the ability to do predictive analytics to more people. And then finally, deploying with a strategy for intervention. Always think about how the data is going to be used to make decisions. And before I cut over to Levi, I just want to talk briefly about what the future holds here. What we see, of course, is that the clinical workflow engine is still the EHR. Clinicians spend most of their time in the electronic health record, and that's where the insights are going to be delivered to them that influence their care decisions. And in today's world, we hear a lot about Smart on Fire. This is a technology that allows the EHR workflow to be augmented through web applications. And Fire is an interface that's designed to sit over the EHR, make it easy to pull live data from the EHR and develop web and mobile applications that, again, augment the workflow of the EHR. Where we see the analytics environment taking place is really providing a lot of power to this idea of putting new applications in the clinical workflow. And the data warehouse really becomes the analytics engine that's driving a lot of the data that shows up in that workflow. So the data warehouse has a host of different data sources that are driving models. Like I said, I referred it to in the beginning as a feature, a chock full of features. We've got registry definitions, we've got text processing, NLP algorithms, we've got all of these predictive algorithms that we're generating, creating almost like an algorithm library. And then we want to expose that through an API such that the real-time data from the EHR through the Fire interface can be combined with all of that analytic data and then deliver that to the web and mobile applications and really not only augment their workflow, but augment the data that they're seeing and make it based on a larger repository of highly valuable analytic data. So I'm going to cut over to Levi now. Levi's going to share with you some exciting news about our software that we've developed. We have decided to open source our software, and Levi will walk you through how you can get to our code repository and download the software and use it for your team or yourself.
Hi, everyone. Great job, Eric. So Eric just gave a fantastic overview of best practices in predictive analytics. So you might ask yourself, well, how can we take it from here? How can we actually do what you guys have described in our organization? And that's why we're so excited to open source this R package we've been working on. So it's called HC Tools, is the overall project. And as you can see here, we're at hctools.org. So if you want to get started today, simply type that into your browser. And the idea is that this enables you to create models on your data with very simple examples. So if we click into the documentation for HCR Tools, it very basically describes why it's so great for healthcare, how to install the package, how to get started with examples. And so let's take some scenario that you might be interested in. So say you have a great data set put together, say it's diabetic data and you're wanting to predict, say, readmissions. So you can ask yourself, well, how does this tool help me do that? So if we hop over to RStudio, after you've installed the package, what you do is you type, okay, well, library HCR tools. So in R, you often load packages in that bring certain types of functionality. And then you simply type $HCR tools, and that will bring up the examples associated with our package. So nice built-in documentation you can immediately use to create a model. So once you have a data set, you click on this, say, lasso development or random forest development link, and that will give you both the descriptions of the arguments to the function as well as the example code. So what you can do is scroll down and you can play with a built-in data set, but let's say, okay, well, you have your data set already ready to go. And so what you do is just basically grab this example code and open up a new script, drop it in, and hit run. And what it basically will do will tell you for this particular data set how well your model did. So you have a lasso model, which Eric had mentioned, and you see the AUC is 0.86, so that's a measure of the accuracy, say for predicting 30-day readmit flag. And then you have a random forest example as well that had an AUC of 0.82, and so you're able to quickly see, okay, well, for this particular data set, we had this particular model that did really well, and so if that's the random forest model, you simply use the documentation to go and deploy that model, and you can see the links there. So as you have your data put together, please visit the website, reach out, let us know what you're working on and how we can improve these tools, because we really want to build a place where we can all collaborate and build something that helps everyone in healthcare.
Thanks, Levi. So again, the URL to go to if you want to download the software is hcrtools.org. Sorry, hctools.org. That was my mistake. We will be renaming and redirecting the URLs at some point to a more marketing-friendly name. Our marketing team has informed us that this is the kind of name that you get when you get a bunch of data scientists into a room to name a product. So we will be renaming it eventually, but hctools.org. Please go there and give us your feedback on the software. If you want to download it and play with it, make it part of something that you use in your organization. We're happy to answer questions and provide that tool for you.
All right, that's great. Thanks, Eric. Now we're about ready for our Q&A time. We've got some good questions in. But while we have those questions in, we do have a final poll question for you. While these webinars are intended to be educational, we've had many requests for more information about Health Catalyst, who we are, what we do. If you are interested in having someone from Catalyst reach out to you to schedule a demonstration of any of our solutions, please answer this poll question now. And while you're answering that, we'll go right to the first question that we have. We've had a lot of questions about why people are not yet using predictive analytics in healthcare, why healthcare seems to be behind other industries, whether it may be contract risk or other reasons.
So that's a great question, and I think a lot of it comes down to the risk reward. It is riskier to start, and I think that we are very risk averse, of course, for good reason, risk averse industry. And I look at the predictive analytics that are delivered to me in Netflix. They're the wrong analytics. I don't care about those cartoons that are being suggested to me. And all of that has to do with assumptions that we're making on the data. And I think healthcare, of course, still has a lot of issues to work out with trust in the data and the underlying quality of the data. So organizations, I think, who are wary to use predictive analytics may also be wary of their underlying data quality. Data governance is a topic that we hear about a lot lately, and helping organizations to actually improve the quality of their data as part of a data strategy is going to be very important for the increased adoption of this technology and these algorithms.
We do have time, looks like, for 2 more questions. Next question is, what are the system requirements to use the HC tools, the HCR tool set that you've got?
Yeah, that's a great question. So if you have R installed on your machine, you can simply visit hctools.org and follow the quick install guide. It's just a few simple commands, and that should get you up and running.
All right, we have another question. Can you integrate R models developed outside your organization or outside of Health Catalyst?
Absolutely. The code base is designed to run. It's designed to allow you to develop your own models. So as long as you get your feature inputs in such a way that the software can address it, the software will help you develop your own models and either make those available to somebody publicly or just leave them in your own environment. The tool definitely supports running and creating models from Health Catalyst as well as creating your own.
Our next question, is there an API that you have to deploy?
No API is necessary. So basically you install the R package and you can use the built-in documentation or the documentation on the web page you see here. And it will have some built-in data actually that you can use to start with. So the examples run right out of the box. And then you can use those examples to tailor them to your specific data and your tables and databases, et cetera.
Okay, we have time for one last question, and that is, can you please share some of your experience in terms of demonstrating the value of predictive analytics?
Absolutely. So whenever we develop models and deploy them with a customer, one of the things that we track is outcomes. And we have, in each of our applications, we have tools to track the variation in those outcomes. And we look for, that's another area where our data scientists and analysts are very helpful, is helping to understand that trend. And is that trend actually going down since the implementation of that predictive model? So we do have ways to measure that. The other thing that we do is we make sure that as we're deploying them, that there's an organizational understanding of how to use them. That's actually very critical in creating that value.
All right, well, we are at the top of the hour. There is one last thing asking if you're not using the Health Catalyst data warehouse and BI platform, can they still utilize these models?
Yeah, for sure. So it's very flexible. So if you have CSV files or a database, you can connect to any of those.
But we want to be clear, you can use the software. The models, specific readmission models do not come with the software. The software is just for running and creating those algorithms.
All right, well, thank you so much, Eric. Thanks, Levi. I'd like to let everyone know shortly after this webinar, you will receive an email with links to the recording of the webinar, the presentation slides. We'll have the link to hctools.org and also an audio download. Also, please look forward to the transcript notification that we'll send you once it's ready, and also the special invitations to the upcoming webinars in the Predictive Analytics webinar series. On behalf of Eric Just, Levi Thatcher, as well as the rest of us here at Health Catalyst, thank you for joining us today. This webinar is now concluded.
Thank you. Please stand by.